Below are the hypotheses for a hypothesis test stated in symbolic form by a student who recently took introductory statistics. The sample mean of 100 cases used to implement the hypothesis test is x bar equals 4.2. Which of the following statements are accurate? Either one, this is only a one-sided hypothesis test. Now for that we can look at um, the not equals symbol here, and that should indicate a two-tailed test. So it could not be a one-sided hypothesis test. So we can eliminate the first option from our possible choices. 2, the claim being tested is always about the population, not the sample. So what? So X bar should not be used to state the hypotheses. This is true. Okay, so option 2 is a good choice, although it may not be the only choice. But remember, what are we doing? When we're doing hypothesis testing, we're interested in understanding something about the actual population by using statistics to infer something. So we use our sample statistics to get an idea of whether our claim makes sense, but the claim is not about the sample statistics. It's always about the actual population, the original entire whole population that we're interested in. So now we should not be using a sample statistic symbol, okay? The sample mean is x bar, is denoted by x bar. The population mean is denoted by the Greek letter mu. So that's what we should see here in our hypotheses is the Greek letter mu, not the x bar. And third option, which also could be part of the answer, says that the value used in stating the hypotheses should be 4.2 instead of 5. Okay, so 5 is there, but our sample mean was 4.2. So should we have 4.2, the sample mean, in our claim? For the same reason that we don't want the X bar in there, we don't want 4.2 in there. We don't want sample information in our hypotheses. So 3 is also not a good option. So the only one that's good here is option 2, and that is the correct answer, only option 2. Okay, another question here is to calculate or construct a confidence interval to estimate the population proportion P. So we're going to put our lower boundary here and our upper boundary here. And we would always start with P hat and then calculate a margin of error to go up and below and above by a certain distance using a certain number of standard errors. And we decide how many standard errors to do using the confidence level. All right, so all of that together, what we need to do is figure out how to estimate p hat, the population proportion, which is our best point estimate that we will use to begin subtracting and adding margin of error. And we also need a formula for calculating the margin of error. So if we look at our formula packet here, we have some choices here up at the top where we've been learning how to use these 3 sections here. So this is for a proportion and it's for a confidence interval. Confidence intervals are along the left portion of this form here. So we're looking for a formula for the confidence interval. And notice that all these confidence intervals are point estimate plus and minus the maximum margin of error E, right? So that's how they're set up. So P hat plus or minus this value, that's your margin of error. Okay, so the margin of error formula is this right here. Okay, so what we want to do is just take that and so now that we have our formula, we just want to collect the parts that go into the formula from our homework problem. So we're going to put that side by side with our spreadsheets. Oops, wrong one. Side by side with our spreadsheet. There we go. And what we need to figure out is p hat. Now, Usually they'll give you p hat somewhere in the problem, like they'll tell you a proportion, a sample proportion of successes somehow. And here they've told us that we have 200 people in the sample, so we know that's n. And then 186 of those had kids. Now, that's not giving us a percentage or a proportion, but certainly we can use the number of successes to figure out the proportion. The successes are 186 out of 186 divided by the sample size n. All right, so p hat, remember, is always your number of successes, x, divided by the sample size. Makes sense, right? I mean, how else would you figure out a percentage? Should be natural, right? Sometimes we don't feel like statistics is natural, but that is supposed to feel natural. How many successes divided by how many total in the sample, then you get your p hat. Q hat is always 1 minus p hat. Okay, so now we have p hat, we have q hat, we have n. We just need the critical value. So we're going to use our confidence level given in the problem, 0.95 as a decimal, to find our significance level alpha, which is 1 minus the confidence level. So this is the area in the two tails in your total area in your two tails if you were to sketch this out, which I always recommend doing. Let's go ahead and just sketch the distribution. It's for proportion. We can see the z-scores here, right? So this is the standard normal distribution, the mean of 0 and a standard deviation of 1. And the critical values, remember, are going to be z-scores on both sides because all of our confidence levels, or all of our confidence intervals, I meant to say, will be two-tailed. So we always take that total alpha and split it in half when we're doing a confidence interval. So half of 0.05 would be 0.025. So we have that area in each of these tails. And then to find the critical value, okay, so alpha half, just call it a half. If you wanted, you could just do it like this, divided by 2, and then get your z, your critical value, z-score, using norm.inverse, right? Well, why are we using norm.inverse? Because we're finding a boundary from a known area. What's the known area? It should be a left area if you're using norm.inverse. So the left area here, 0.025, which is our alpha half, right? The mean of 0 because it's a z-score, and the standard deviation of 1 also because it's a z-score. And notice that it gives us this negative answer, negative 1.959, or approximately negative 1.96. And that means that the positive version of that is going to have an area to its right because the bell curve is symmetric. So if we have 0.025 in the left tail, then this boundary would be negative 1.96, and it's matching on the right side so that if this right area is 0.025, then this boundary should be positive 1.96. Okay, now we always want to use the positive version when we're calculating a margin of error. So I've encouraged you guys when doing confidence intervals to put absolute value around just to keep it positive. Okay, then you also want to look out for any rounding because sometimes the directions will tell you to round your critical value before using it in your margin of error formula, but here we don't have any directions like that, so I'm not going to round it. I'm going to leave it like it is. And so now we have the last missing piece of our formula. So now we're going to calculate E. Okay, so E, the margin of error, is the critical value times the standard error, which in this case is square root p hat q hat over n. So we're going to take approximately 1.96, although don't round it unless you're told to. I'm just rounding it so it looks neater as I'm writing it out. Same thing with p hat and q hat. 0.93 times 0.07. Those are nice and nice little, they don't have to be rounded. But if they were like long decimals or anything like that, don't round them. Just use, it's best if you use Excel and you can actually refer to those values directly. And then divide by n, 200. All right, so I'm going to be calculating that here, my margin of error, my z-score, not rounded, times the square root of p hat times q hat divided by n. And there's my margin of error. Now, to construct my confidence interval boundaries, okay, where p is, we're estimating the true population proportion p to be in between these two values. Well, it'll be my p hat, the sample proportion, minus the margin of error, and my p hat sample proportion plus the best point estimate plus this margin of error. So with 95% confidence, we believe that the true population proportion is between 0.894 or 0.895 approximately and 0.965. So now we can go ahead and enter this with decimals to 3 decimal places, 895 and 0.965.